If you've ever used the Unity profiler, you may have noticed that, in addition to the main thread, Unity also creates additional worker threads, one for each additional core in your system. The profile shown here, for example, is running on a computer with 8 cores and so has 7 worker threads. The worker threads are utilized by some Unity internals, but you can also run your own code on these worker threads using the C# job system. What we call a job is simply a unit of work to be executed on the worker threads. Here's perhaps the simplest possible example, a job that computes the square of every number in an array. The job is defined as a struct type implementing the iJob interface, which has one required method, execute, which will be invoked when the job is run by one of the worker threads. In this execute method, we're looping over the array and multiplying every number by itself, effectively squaring all the numbers in the array. Notice that the array here is not a normal C# managed array, but rather an unmanaged native array from the Unity API. While it's not strictly impossible to use managed objects in jobs, doing so safely requires special care, so normally your jobs should avoid accessing managed objects. Besides, managed objects are not allowed at all in burst compiled code, so this job must avoid managed objects entirely if we want to get the benefit of burst compilation. To run this job that we've defined, we need to instantiate and schedule it. Assume on the right here that we're in the context of some main thread code, such as a MonoBehavior update. We first create an instance of the job, setting its nums field to the array whose numbers we wish to square. We then call the extension method schedule, which puts the job instance on the global job queue, and then at some point later when an idle worker thread looks at the queue to find more work, it can pull this job off the queue to run. At some point after scheduling any job, the main thread should call complete on the job handle returned by schedule. Calling complete does a couple things. First, if the job hasn't already finished execution before the complete call, complete will sit and wait for the job to finish. Either way, the complete method will not return until the job has finished execution. Effectively, complete is used to synchronize jobs with the main thread. The main thread calls complete on a scheduled job once it needs the work to be finished. The other important thing that complete does is it removes all record of the job from the job queue. So completing all scheduled jobs is required to avoid a resource leak. Now, an important limitation is that jobs can only be scheduled and completed by the main thread. Jobs themselves cannot schedule or complete jobs. Another important restriction to keep in mind is that the main thread should not access data that's in use by currently scheduled jobs. For example, in between scheduling and completing this job, the main thread should not access the contents of the native array that it uses, and in fact, attempting to do so throws an exception thanks to runtime safety checks. Only after the job has been completed is it safe for the main thread to access the contents of the array again. Now, let's say that we want to run this job twice using the same array. Here we've instantiated the job twice, setting the nums fields of both to the same native array. When we then try to schedule these two jobs, the second schedule call throws a safety check exception. The fact that these two jobs are instances of the same type is incidental. The problem here is that the second job we're trying to schedule accesses the very same array as an already scheduled job. Allowing two jobs that access any of the same data to execute concurrently would represent a race condition, so safety checks in the schedule method throw exceptions if the new job accesses any data that's also in use by any already scheduled job. To fix this, we could simply complete the first job before scheduling the second. Doing so would effectively guarantee that the first job runs and finishes execution before the second job runs, thus avoiding the race condition. On the downside though, this would require the main thread to sit and wait for the first job to finish execution before scheduling the second job, which would be a waste of the main thread. The better solution here is to make the first job a dependency of the second by passing its handle to the second schedule call. As a rule, the worker threads will not pull a job off the queue until after all of that job's dependencies have finished execution, and the safety checks understand that a job does not conflict with its own dependencies. Effectively, job dependencies allow us to set an execution order amongst our jobs when required. Now, dependencies can themselves have their own dependencies, so we can form dependency chains like this one. The arrow points in the direction of dependency, so job D here depends upon C, C depends upon B, and B depends upon A, making the effective execution order first A, then B, then C, and last D. We're not limited, though, to just simple chains. Here, B, C, and D all directly depend upon A, so until A finishes execution, B, C, and D must all wait. Once A finishes, though, B, C, and D can all run without waiting for each other. It's also possible for a job to have multiple direct dependencies. While the schedule method only takes one job handle as input, we can logically combine handles with the static method combine dependencies. Here, we schedule job A, passing a handle that's a combination of B, C, and D. So A must wait for all three of these jobs to finish execution, but B, C, and D can all run without waiting for each other. Our scheduled jobs can in fact form complex dependency graphs like this one. In this graph, job D, for example, depends upon A, B, and C, but D itself is the dependency of E, F, G, H, and I. Meanwhile, job I in this graph depends upon all the other jobs with the exception of E and F. Earlier we said that every job should eventually be completed, but understand that completing a particular job also recursively completes all of its dependencies. That means then, say in this graph, that we don't need to call complete on the handles of all the individual jobs, only the handles of E, F, and I. Also understand that calling complete on an already completed job is a harmless no-op, so you don't have to worry about redundant completions. Lastly, note that we wouldn't ever want to create cyclic job dependencies because that would create deadlocks. For example, if a job A depended upon a job B, while at the same time job B depended upon job A, then both A and B would be stuck forever waiting for the other. Fortunately, you don't have to worry about such cases because a job can only depend upon jobs that were scheduled before it, and once scheduled, a job cannot change its dependencies. These two facts together make it impossible to schedule cyclic dependencies. In some cases, the elements of an array or list processed by a job can be processed in parallel. In our squares job, for example, the elements of the array could all be safely squared concurrently with each other. To parallelize this work, we could manually split the work across many separate jobs, but a much better solution is to use the iJobParallel4 interface. When this iJobParallel4 runs, its execute method will be called once for every index of the array, with each call processing just a single element, the element at the index passed to the int parameter. Indexing the array with any other value, in fact, throws a safety check exception. When we schedule this iJobParallel4, we pass the length of the array and we pass a batch size, which determines how the indexes of the job get split into subranges called batches. The worker threads then can grab these batches off the queue, and so separate batches may be processed concurrently in separate threads. In this example, if our array length is say 250 and our batch size is 100, then the job will be split into 3 batches. The first covering indexes 0 through 99, the second covering indexes 100 through 199, and the last batch covering the remainder, indexes 200 through 249. Because the job is split into 3 batches, it will effectively be processed at most across 3 worker threads. If we wanted to split the job up across more threads, we would have to pick a smaller batch size so that it gets split up into more batches. Now, the choice of a good batch size isn't an exact science. In the extreme case, we could pick a batch size of 1 and thereby split each individual index into its own batch, but keep in mind that having too many small batches might incur significant job system overhead. So, in general, you should pick a batch size that seems not too big but not too small, and then experiment to find a size that seems optimal for each specific job. Anyway, if I now run this job with an array of 10 million integers using a batch size of 100, the job takes approximately 3 milliseconds from start to finish, but 24 milliseconds in total CPU time spread across my 8 cores. So this seems like a victory for parallelization, because for the duration of the job we're keeping all the cores busy. But see what happens if we specify a batch size equal to the length. That means the job is divided into just one big batch, and so will only run on one core, but perhaps surprisingly, the job takes the same 3 milliseconds from start to finish. How can a single core do the same work as 8 cores in the same amount of time? Well, recall that this job is doing just a single multiplication per element of the array, which is a trivial amount of computation, so the real bottleneck here is memory access. When we split the workload across 8 cores, those 8 cores all must contend with each other for memory access, and so 8 cores can't read and write the array any faster than a single core can. In a case like this then, we're better off sticking with a single-threaded job. However, in other cases that require more computation per byte of memory accessed, parallelizing the work can greatly improve performance.